Today we talk about so-called 2D kinematics, where we extend our study of constant acceleration and constant velocity motion to the kind of equations that you can use for any object moving near the surface of the Earth. That is, constant acceleration in the vertical direction and constant velocity in the horizontal direction. So we'll start that out just by talking about how those equations come about, that if you consider the general case of constant acceleration, where acceleration is a vector, meaning a vector of constant magnitude pointing in a constant direction. The most familiar case of this is gravity, where g, the acceleration due to gravity, is a vector that points down with magnitude 9.8 meters per second squared. So it turns out that if you have constant vector acceleration, then you get a set of equations like I described a moment ago. And then we'll do two examples. So these should be familiar based on our work that we did for motion along a line and the beginning of the study of free fall, where we just talked about objects moving vertically. But we'll extend that to objects that can move both vertically and horizontally near the surface of the Earth. And then next time we'll consider so-called projectile motion, which makes it just a little bit more general, allowing for initial conditions that are not necessarily horizontal or vertical. So we'll spend some time doing this 2D kinematics. So let's just look at it theoretically first. Let me remind you of the equation for an object that is moving along a line with constant acceleration. So we could call that line the x-axis, and maybe the object is like a car or something. So here's our car, and maybe it's coming to a stoplight, so it has some velocity vector that looks like this, but it has some acceleration vector that looks like this. So if you want to do that problem, then you would write down the equation, for example, for the position of the car, the x value, as a function of time, and we found that that was x of t is equal to x at t0, meaning at t is equal to 0. Then you add in the initial velocity in the x direction, multiply by time, and then you have 1/2 times the acceleration in the x direction, t squared, so the x component of the acceleration. So that's our equation for position when you have motion with constant acceleration. Now we could generalize that to an acceleration vector and to a position vector. And remember that these equations, vector equations, just separate out into x, y, and z components. So you can imagine that there's a y of t equation that looks exactly the same and a z of t equation that looks exactly the same. And if you add all those together with their unit vectors, then what you would get is the position vector as a function of time. So maybe we could look at the same object, but as measured from some other coordinate system. There's our position vector. The position vector as a function of time is equal to the initial position vector, so that's r at time 0, plus the initial velocity vector times time, plus 1/2 times that constant acceleration vector times time squared. So you see that that's basically that if I wanted to find the x component of this equation, it would be exactly this, right? Take the x component of r, that's x. The x component of the initial r, that's x0. The x component of v0, that's v0x. A goes to ax. So this equation is true. This is for constant acceleration motion, but now we can consider it in the case of a constant acceleration vector. And this is exactly what one would need for the case of free fall, so-called free fall, meaning the motion of objects near the surface of the Earth where we have a constant gravitational field, meaning that all objects have an acceleration that points downward with magnitude g, 9.8 meters per second squared. So let's just draw a little picture of that. So maybe we have baseball player. Oops, I don't know what happened to their arm. Baseball bat. I guess the bat should have base swung already. There, they've swung the bat, and now we have the ball. And so the trajectory of the ball might look something like this. So at this particular moment, velocity vector points along the path. So this is the velocity vector of the ball. But the acceleration at any moment along that path is exactly the same, and it's this vector, A, which I can write, I could label it just with its magnitude, and its magnitude is g. So it's an acceleration vector that points down towards the center of the Earth, and it has magnitude 9.8 meters per second squared. So what does that mean for solving problems? Well, we could choose a coordinate system. Maybe we could put a coordinate system right at the initial place where the ball was hit. So here's a y and an x-axis. And we could look at our motion with constant acceleration equation. And then we could break that down into its component equations. So in the x direction, this would be r sub x. So in the x direction, it would be r sub x, but we just call that x. And then we get x naught. And then we have to find v naught x. And then we have 1/2 ax t squared. And similarly, we would have a y equation, which is y of t is equal to y naught plus v naught y. Notice that I'm just looking back up here, finding the x component and the y component of each vector. And so that becomes v naught yt plus 1/2 ayt squared. So far that's just repeating what I was saying above. But now we can actually look at our situation and say, oh, so I have an acceleration vector, and it only points along the y-axis. So that means that its x component is equal to 0, right? If we place the a vector on a coordinate system here, then this number, a sub y, is minus g, but its projection back to the x-axis, this number, is 0. So a sub x is equal to 0. So I could plug in here that I get x of t is equal to x naught plus v naught xt plus, 0. It leaves me with the constant velocity equation in the horizontal. And then I could plug in down here, y is equal to y naught plus v naught yt plus 1/2, and then ay, well, we found it to be minus g t squared. So our motion in the vertical direction becomes the constant acceleration equation. So motion with constant acceleration in 2 dimensions reduces to, or can reduce to, motion with constant acceleration in 1 dimension and motion with constant velocity in the other direction. Notice the way that we got that was by choosing a coordinate system that had a y-axis parallel to the acceleration vector. I could have chosen a y-axis that pointed sort of at a diagonal, and then this acceleration vector would have both an x and a y component, and it would make our equations more complicated. Then I'd have an ax and an ay. So it's a good idea to choose a coordinate system that points along the acceleration vector, either with a y pointing upward or with a y pointing downward. If the y was pointing downward, then this component would then be positive. So I only need to look at constant acceleration motion and constant velocity motion in order to solve problems like this, and they break apart completely independently, so I can look at them completely independently. So let's see what that means, that you can look at the horizontal and the vertical motion independently. So here's an example. We have a gun firing a bullet horizontally. So horizontal is a technical term in physics. It means perpendicular to vertical, and vertical is a technical term that means the direction toward the center of the earth. So horizontal is the way that you make a table. So a bullet is fired horizontally with a muzzle velocity of 500 meters per second. The speed of sound is something like 340, so this would be greater than the speed of sound. And at the same moment, the shell casing of the bullet drops to the ground. So the bullet is fired out of the gun, so let's draw a little picture. I don't really know anything about guns, but something like this. So we have the bullet, which is going initially out of the gun, and it's being shot horizontally, so its initial velocity vector is horizontal, and I guess I could, instead of calling it a vector, I can just label the vector with its magnitude. And at the same moment, the casing of that bullet, so I'm not exactly sure what that means, but the thing that holds the bullet falls directly to the ground. So I probably should have drawn it up here. So it's going to fall out of the gun and fall straight down to the ground. So the trajectory of the shell casing will be just this vertical line. And let's draw the ground, I guess. And the trajectory of the bullet, this is of course not to scale. I guess it won't come in directly vertically. The trajectory of the bullet will look something like that. It will be initially horizontal, and then eventually it will hit the ground at some distance far away. So we could put a distance here. Don't know what that is. We could put a height here, like this. And let's look at the question. The question is, how does the flight time of the bullet compare with the drop time of the casing? So we want to look at the amount of time it takes for the bullet to reach this point here, and the amount of time it takes for the shell casing to reach this point here. So we could say, well, they're both at like position A initially, and maybe I should call this V bullet initial, and this is, and V shell initial is equal to 0. And then the bullet will reach point B, and the shell casing will reach point C here. So I want to look at the amount of time it takes for each of those objects to reach the ground, which is a different position, but it's the same vertical distance downward. Okay, so let's look at the bullet first. So we want to find the time to go from the shooting of the bullet to the ground. We were given an initial velocity vector, and I guess we want to see how long it takes to go along this distance, I guess this vertical distance here. So let's try to look at the vertical equation, and I guess I should give myself a coordinate system. Let's call this the y-axis, and we'll call this the x-axis. So in the vertical direction for the bullet, we have y is equal to y0 plus v0 yt plus 1/2 ayt squared. I should have drawn that the bullet at every moment has an acceleration vector that points downward, which is equal to g in magnitude. So now we can just apply that equation. So I'm going to use this equation. Remember, you want to state how you use it from point A to point B. So from the shooting to the hitting the ground. And then I look and see what I have. So my final y position is what we mean by y. So that's here, but it's the value of y at that position. So I project back to the y-axis and I see, oh, that's 0 based on my coordinate system. My initial value of y, that is up here, and that is this point on the y-axis. Well, that's what I called h. So I can write h. And my initial velocity in the y direction. So I can look at my initial velocity vector, and I can place that initial velocity vector on a coordinate system, meaning the same coordinate system that I've chosen. So here's my initial velocity vector, v bullet naught, and this is the x component, but that's not what I'm looking for in this equation. What I'm looking for is the y component. So if I go from the tip of the vector back to the y-axis, I see that I land at 0. So v bullet naught y is equal to 0. So at this point I can write in plus 0. 0 times time is 0. And then I have 1/2 ay. Well, that's the y component of this vector. You can see that if you place this vector over onto the same coordinate system, that its component would be a negative number on the negative y-axis. So that will be minus g. So what do we have? Does this help us? I guess it does, because we want to see what the time is as compared to the distance that it has to fall. So we could solve this equation. It's going to be h is equal to 1/2 gt squared, or if you solve for time, it's going to be t is equal to multiply by 2, divide by g, and take the square root. So that will be the t fall for the bullet. So let's actually give it a name. T fall bullet, T fall bullet, T fall bullet. Okay? So we found the amount of time that it takes to fall. Now let's consider the shell casing. So the shell casing goes from this point down to this point, so from A to C, and we might as well use exactly the same equation. So we have y is equal to y naught plus v naught yt plus 1/2 ay t squared. State how we're going to use it. We're going to go from point A, back at the gun, to point C, directly below the gun on the ground. And then we just go through and look at what the values are. So final value of y, well, that's going to be the value of y when it reaches this point. That's at the origin. That's at y is equal to 0. So I can write 0 here. Initial value of y, that's up here at the y-axis at this tick mark, and that's exactly what we called h. So I can write h here. Initial value of the velocity of the shell in the y direction. Well, we stated that the total velocity of the shell was equal to 0. So both its x and its y components would be equal to 0. So that means that this will be equal to 0. And then finally we have the acceleration of the shell. Well, because it's free fall, because we're talking about the acceleration due to gravity of all objects near the surface of the Earth, this acceleration vector pertains to both the bullet and the shell. So it will be exactly the same acceleration. So this will be minus g for ay, and this will be t shell fall, t fall shell squared. So this equation becomes h is equal to 1/2 g t fall shell, or t fall shell is equal to 2h over g. Well, look at that. It's exactly the same as for the bullet. So how does this arrive? So the bullet you shoot out you shoot it at 500 meters per second, which means, unlike this picture where this might be a meter, this should be something like hundreds of meters probably. So the bullet goes straight out horizontally, but then eventually starts to fall to the ground. But at the moment that the bullet lodged itself in the ground is exactly the same moment that that shell casing hits the ground when it falls directly out of the gun. Why is that true? Well, it's true because the horizontal and the vertical motions are completely separated. So when I look at the bullet's motion, I don't have to think about its horizontal motion in order to describe its vertical motion. Its vertical motion is completely determined by this downward acceleration, and that description, which is in this equation here, is exactly the same description for the shell, which is just simply falling to the ground. So the horizontal motion of the bullet doesn't affect its vertical motion at all. That's a bit of an idealization. So in physics, we'll often use ideal models to describe a more complicated real-world situation. In the real world, there's actually something called air resistance. So this story that we just told is exactly true for a vacuum, but if you have a bullet that's shot in air, then it will actually feel some backward force due to the air, and that will change its trajectory slightly. Of course, it'll also change the trajectory of the falling bullet, but it happens in a slightly different way. So it might be not completely true that they hit at exactly the same moment. I think that the bullet's trajectory would hit a little bit nearer than is shown on here, and because of that, it might hit slightly, well, I don't want to guess. I'm not sure if it's slightly before or slightly after the shell. You can take a look. Maybe we'll talk about it when we come back to air resistance and forces. Okay, so you can see here that this is a nice example showing exactly what it means that you can separate vertical from horizontal motion. In this example, we have a swimmer diving off a cliff with a running horizontal leap. There's a catch though, so we have a cliff here, and we have water down below at 9 meters below the cliff. But there's a shelf, so more cliff. And that shelf sticks out a little distance, I guess 1.75 meters. So the runner starts back here, and she's going to jump off, and as she goes, she needs to have some initial velocity, and we're told that it's going to be a completely vertical a completely horizontal initial velocity, so a running horizontal leap. So she's going to have an initial velocity that points horizontally, and the question is, what must that initial speed be, so the magnitude of that velocity vector, so we don't know that, in order for her to make it into the water and not die, apparently. So she could have some trajectory that has some initial speed that brings her way out into here and everything is great. She could have an initial velocity that brings her here and everything is not so great. I guess the question is, exactly what is the velocity that would bring her to exactly this point here, where she just misses the cliff ledge. So let's erase those other trajectories, and let's draw the trajectory for her going exactly like that. So she's going to just miss the cliff ledge at the edge of the water and make it into the water. Okay, so we want to analyze this, so we need to have a picture, and I think we need to add a few more things to this picture. So we've labeled everything that we were given. We probably want to also include our acceleration, because that's the main point here, is that the acceleration due to gravity points down with magnitude g. We're going to want to use a coordinate system. So remember, you can use any coordinate system you want, but as we showed on the first page here, it's good to choose a coordinate system where the y-axis points along the acceleration vector, so probably up or down. Why don't we choose down this time, just for the heck of it? So I'll choose this as my y-axis, and I'll place the origin at the initial jumping position of the swimmer. So I could have put it down here, that's what we were doing before most of the time, but I just want to show you that we can use a different coordinate system and we'll still be able to answer the problem. Okay, I think that's enough. So this is sort of our first example of a projectile motion problem. Projectile motion is just the word to describe objects in free fall which might be moving in two-dimensional space. And so in general in these problems you're going to need to write down equations for the motion in the vertical direction, which will be constant acceleration motion, and also equations for motion in the horizontal direction, which will be constant velocity motion. And generally you'll have to put those equations together. So you probably shouldn't expect that you're going to be able to write down one equation that has one unknown that you can solve for a number and then plug that into another equation. Sometimes that might be true, but more often, or more generally, you'll get two equations with two unknowns. And of course the sequence is you'll get one equation with two unknowns, and at that point you need to make sure you don't panic. You just start writing down another equation which has an unknown as well, hopefully the same unknowns. Then if you have two equations, two unknowns, in algebra you can solve for that, so you can solve for everything that you need. So the method, after drawing your picture, after choosing a coordinate system, is simply to start writing equations down that describe the motion of the object. And as before, we should probably choose to name some points. So let's call the jumping off point point A, and let's call the point at which she hits the water just past the ledge point B. And let's write down one of our equations. So let's say first, let's use the y equation. And I want to apply that for the motion from A to B. So let's give it time here. Let's call this the time that she hits the water. And time 0 will be the time that she leaves the cliff. Okay, so what is our final y position? So we have to look at the B point. And what is the y value of that B? Well, we project back to the y-axis. So it's this number on the y-axis. So is that positive or negative? Well, I chose this to be the positive y-axis. So that's a positive number. And it's h away from 0. So the value is simply h. What is my initial y value? Well, that's back here at point A, and that's at the origin, so that's just 0. What is my initial velocity in the y direction? What's the y component of my initial velocity vector? Well, you can see it here. This is a horizontal vector, so it has a 0 y component. But let's be explicit about it. Pretend we don't see that. And let's just draw our vector on our chosen coordinate system. So here's our v0 vector. This number is called the x component of that velocity vector, and we can say that that x component is just equal to the magnitude of the vector. But if you project backwards, back to the origin, you find when you hit the y-axis you're at 0, so v0y is equal to 0. So finding the components of a vector on our chosen coordinate system. Notice that I drew my coordinate system here exactly the same as the one that I chose for the big picture above. Okay, so v0y then we find is 0. 0 times time is 0. and then we get 1/2 ay. So now we have to find the y component of the acceleration vector. Let's just do that again. So here is our xy coordinate system. I usually draw a separate one for accelerations and velocities because they don't belong to the same space. Accelerations are in meters per second squared and velocities are in meters per second, so you shouldn't be drawing them on the same coordinate system. So what is the y component of the acceleration? Well, it's this number, and ay then is equal to positive g. And it's positive now because I chose my y axis to point down. So when I go back to my equation, I just plug in g for ay. And then I have the time at point B, and that is what we call t hit squared. So, am I able to solve the problem? Well, I just told you we'll have multiple unknowns per equation, but it looks like in this equation we have t hit is equal to 2h over g square rooted. So I could actually find a number for that just by plugging it into my calculator because I was given the value of h and I know the value of g. Let's not plug it in quite yet. Let's look at the next equation. So I've used h. I haven't yet used d. So let's write down an equation where d would appear. Well, that's a horizontal distance. So I could write down the equation for the diver's horizontal position. If you want to, you could write a plus 1/2 ax t squared, and then you see, when you look at this acceleration vector, you see, well, it has a 0 x component, and therefore this term goes to 0. But you can also just write down the constant velocity equation for position. Okay, next step, we choose how to use it. So I'm going to use it exactly the same way as I did above, from point A to point B. So what is my final x position? Well, I look at point B, and I find out what is its value along the x-axis. So I project back to the x-axis. I'm looking for this distance. Well, that's exactly this distance d that we are given there. So the final x position is d. The initial x position, just as before, we're starting at the origin, so the initial x value is 0. And then we have the initial velocity's x component. So we already found that. If we look back at this coordinate system, if you place the initial velocity vector of the swimmer on the x-axis, you see that it has an x component equal to its length. So we can write that simply as v0. So these two numbers here are different. This is the component of the vector, which could be positive or negative number, and this is the magnitude of the vector. So what I'm saying in this step is the component of the vector in the x direction is a positive number equal to its magnitude. Just like I said, the component of the acceleration is a positive number equal to its magnitude in the y direction. And then we have the amount of time it took to get to point B. Well, that's exactly what we called t hit. So that means that I could find, so what can I do? Well, I guess I know d. From above, I know what t hit is, so v0, the speed, is my only unknown. So it looks like I'm done with the problem. We have v0 then is equal to d over t hit. So let's plug in our numbers and figure it out. Gotta go to my calculator. So we have t hit is equal to the square root of 2 times h, which is 9, divided by g, which is 9.8, and that will be 1.36 seconds, approximately. And then if you plug that into the next equation, we have v0 is equal to d over t hit. So that is going to be 1.75 divided by 1.36, and that's 1.29. And that will be in meters per second. So that's the answer to the question. We were asked, how fast must she go at this point in order to not hit the ledge below? And the answer is a little more than a meter per second. Remember that from meters per second to miles per hour, it's like a factor of 2. So that means that it's probably around 2 or a little bit more miles per hour that she needs to go, which is not that fast. You know, you can walk fast at 4 miles per hour. So in case you were worried, seems like she's going to make it, unless she like slips up here or something like that. Okay, that's our first experience with projectile motion. Next time, we'll study some slightly more complicated projectile motions. One example of that would be if the swimmer decided to not only leap horizontally, but also push off and go in the vertical direction like this. So we'll leave that for next time.